Good. I think we got everybody back here. So I hope you met some new people. I hope this is the beginning of a new friendship, and also that it's the beginning of a new network, which is really the whole reason for having this workshop in the first place. As I said earlier, we have 3 sessions today, 2 before lunch, 1 after lunch, and the 1 after lunch is relatively short. I'm going to transfer control over to the first chair, Jeremy Sikar from Elaria High School, who will be chairing session 4 on teaching physics. Jeremy, over to you.
Thanks, Eric. Our first speaker for today is Nikolai Sonov from the World Youth Academy in Bulgaria, and he's going to be speaking on creating experimental staging in physics.
I offer you implementation of engineering design in training physics experiment. The most important problems in learning physics in the school are, first, lack of the time for experiments, and second, not enough working place. And that's why very often teachers only make demonstration 1, 2, or 3 in front of the students. But with 3 demonstration, we couldn't calculate statistical mistakes. That's why I offer you solution of these problems with engineering design in experiments. How? For example, in mechanics section, pendulum and lever systems, I solve problem in this way. I decide to find time. How? I steal time from the other classes. In our way, in our case, in technological classes. I ask teacher and students to make in technology classes stand for pendulum from wooden profile, and not 1 pendulums, but 5 pendulums. So we decided problem with not enough places. Already we have 5 working places, and we divided the time while we making construction of the working places and the time when we make measure. That's why in 7th grade in physics classes, when we measure period and frequency of the pendulum, we have enough time to make enough measure. How? I divide the class in 5 teams. First team on the first places, second team to the second places, and so on. And on every 1 places, I put checklist, and first team make 10 measure and write them on checklist. Second team on the second checklist, and so on. After that, I switch teams. First team go to the second working place, second team to the third working place, and so on. And everywhere they make 10 measure and write their values on working place or on checklists. So at the end of the experiments, on every 1 places we have 50 measures in checklists. One wrong measure is only 2% mistake. This is not bad. But this was first goal, to solve problems with time and working places. Second goal was advertise physics as interesting science. How? You remember that students in technology classes write on their stands their names. And when they go to 6th grade and working with level system, but with their stands, their own products, they are signed, do you know? They will be a little more proud. In 7th grade, they will measure parameters of pendulum with their own products, their own stands. And they again will be a little more proud. In high school, they will measure earth acceleration with pendulum using their stands. And they will be a little more proud for third time. And at the end, in the high school, I think that at least a few % of students will think that physics is not so boring science, but physics is good, cool science. That's why I think that at least a few % of them will study physics in university. Why not studying for physics teacher in university? This is my way to increase capacity of physics teacher with engineering design in trading physics experiment. But where everyone letter in our project as science in experiments in physics classes. Science is physics and mathematics. Every one calculation is mathematics. The technology classes, they make our stands, lever, and pendulums. Engineering, these students in 5th grade, they can find something better to do with their stands or projects in 6th, 7th, 9th class. Thank you for your attention. See, please, short video.
По дефиниция разглеждаме технологиите като практическо приложение на научното знание за нуждите на човешкия живот. Днес в часа по технологии и предприемачество ще изработим макет, който служи като стойка на пружинно махало. Математическо махало и махало на Галилей. Необходими са ни един квадратен дървен профил с дължина 150 см, който ще разрежем на 3 равни части и ще образуваме хиксобразната стойка с тези отделни части. Когато я конструираме, трябва да получим равностранен триъгълник със страна 25 см. След това ще добавим опорните кръчета и горната част на нашия макет, опората за кукичката, върху която ще монтираме махалото. Започваме да разкрояваме дървения профил, като внимаваме да режем правилно, да движим ножовката от край до край. Давай, точно така. Получихме... Какво получихме? Трите елемента на стойката, която трябва да образуваме сега. Сега нека да сглобим. монтирахме и кутичката и с това приключихме работата си за днес.
Science в контекста на STEM образованието представлява наука, разглеждаща всички основни закономерности и закони в природата. Благодарение на формулата периода е равен на 2π корен квадратен от L върху G, ние можем да стигнем до втората формулка за линейна връзка между дължината на нишката и квадрата на периода на махалото. Ще построим линейната зависимост между всички точки, които сме построили на графиката, на ръка, и ще може да изчислим константата 4π квадрат върху G, чрез което може да изчислим и нашето земно ускорение с достатъчно добра точност. Това е задачата ни за часа. Започваме работа. Изменението не трябва да бъде повече от 8 градуса.
4, 15, 16, 17, 18, 19, 20.
Добре. Значи сега направихме 20 пъти измерване на периода. Времето ще го разделите на 20 и изчисляваме t. По формулата ние може да изчислим коефициента 4π квадрат върху G. След като начертаем апроксимиращата права на милиметровата картина.
Thank you, Nikolai. And I just want to say before we get, I see Marcy has her hand raised. And if anybody else has a question, then please do raise your hand so I know to call on you. But I just wanted to reiterate something I saw a couple of times in the chat, that that idea of building a sense of pride in your work makes such a huge difference in terms of feeling good about taking the course. And when we feel good about taking the course, makes us want to work harder, makes us want to succeed. So Marcy, do you want to unmute yourself and ask your question?
Sure. Well, first, let me say I'm super impressed with the linearization of that equation with middle schoolers. I thought that was really amazing. But also, I was going to ask you,
Yes.
did you have any trouble with getting other teachers on board? I think it's a great idea to get them involved building stuff, but did you struggle to get the teachers involved in doing that?
No, it's not so boring. Otherwise, for them was very, very interesting, because little students haven't enough manual literacy. They couldn't work with screw, a little drill, and so on. That's why for them was very, very interesting. And for me was very important to calculate statistical mistakes, because otherwise they couldn't calculate statistical mistakes. But we made 50 measures. One wrong measure is only 2% mistake. Do you understand?
Yeah, so you're saying that by having multiple groups work on the same stand, you were able to get more statistical error, so you could analyze that with your students, right?
Yes, we use the same stand. If we put lever on the stand, it will be lever system. We put only a few holes, and this is lever. But if we put thread with weight, this is already pendulum. That's why we need only stands. But while they made stands, we speak about pendulums. We speak about Galileo Galilei and how he can predict that Mercurium will spin around the sun quickly than Earth. That's why we speak in the technology classes for physics, but not for technology. This was very interesting for them. Hello.
Thank you. I see we have another question from Shu Yi. Can you unmute yourself and go ahead and ask?
Hi. I think it's so interesting that it brings me to think about this idea of the maker movement. A lot of students talk to me after they graduate and they go to school. They say, I wish I do a little bit more hands-on stuff, being able to design my apparatus, being able to test different things, and being able to use the tools. And I think that's one thing that's lacking a lot in terms of how we kind of compartmentalize the different disciplines in the certificate process, whereas physics teacher has these standards and technology teacher has a whole different set of standards, and it's interesting how you kind of pull it together. I wonder if you can talk a little bit more about other projects that you do where it's a collaboration or students are really learning to use the tools earlier on to use them in the classes.
I understand you that it is interesting like a project. Yes, it was very interesting like a project. For example, the face of this stand is not mine. I thought at the first time that the face have to be T form. T, like a letter T form. But students offer to be X form, and this is better. That's why we use this form, and this is engineering, but their engineering, not mine. That's why interesting when we make students doing some in technology classes.
And I thought that I had seen another hand up that I hadn't gotten to call on yet, but it's disappeared. So if you had a question and you haven't had a chance to ask it yet, if you could please re-raise your hand. Kelly?
Yeah, thank you. Yeah, thanks for the great presentation. I was wondering, I don't know if I missed this at the beginning, but so how long do you spend with the students working on the same sort of system? Like is it sort of like a project that you'll work on for like several weeks, or like what's the time scale for the middle school students?
No, students don't make only stands. They make all of the system. Stands with thread with weight for pendulum, stand with lever for lever system. That's why they made two systems at one moment. But stand is multifunctional.
Okay. Okay.
Do you understand?
Yeah, I think so. I think so. Yeah, you're using it. You're like incorporating it.
But when stance is the common, we make only 5, but not 10 for experiments with lever system and 5 with experiments from pendulum. If we divide it, we have to make 10 stands. But we made only 5, and first of all, we used them in lever system, and after that, with pendulum system.
Okay, I get it. Okay, it's very cool. Thank you.
You understand?
Yeah, I think so.
Do you understand?
I think.
Okay, okay.
Thank you.
And we've had a really nice chat going on with people talking about different ways that they use laboratory work to hook students from the start. We do have time for another question. If anybody hasn't had a chance to ask a question or they were afraid that we'd run out of time, please do put your hand up. So one other question that I have for you then is we have a 5-minute break coming up and we can go whichever way the group likes. If you would like to have a real break or if you would like to go into another breakout room, could you just click yes if you'd like to go into a breakout room and meet some new folks, or click no if you would rather just have a 5-minute break away from your screen?
One moment. I'd like to...
Jeremy, it's about a 2 to 3 yes, no. So what I could do would be to make breakout rooms with 5 people, and the people who don't want to join the breakout room just don't join them or leave them. And people who want to be in the breakout room should end up with about 3 people in the breakout room. Does that sound like a fair solution? This way everybody gets what they want.
Yes, I think so. Although first, I would like to just thank Nikolai, and also I think he had one last thing that he wanted to say. Nikolai, was there something else you wanted to add?
Yes, I hear you, but I lose my video. I lose my face on the Zoom window. I just hear you. Do you see me?
Can't see you, no, but we can hear you, and we appreciate your presentation this morning. Thank you very much.
Thank you. Thank you.
It is time now to turn our attention to Chaz Dermer from Marion Steele High School in Amherst, Ohio. He's going to be speaking on modeling instruction, strengths and weaknesses.
Dermer. I'm a public high school teacher in Amherst, Ohio. I've been a teacher for 30 years, and I have over 15 years focused on physics, calculus, AP physics, mathematics. Mathematics I've been teaching since the very beginning. I've been teaching freshman physical science for 25 years, and I developed a conceptual science course here that we call practical science. I've been a modeler since 2006. I took a modeling workshop here in Ohio, which is where I live, under the auspices of Dr. Kathy Harper of Ohio State. And I kind of, as we sometimes put it, and it's not in, doesn't have a entirely positive connotations, but I drank the Kool-Aid. And then I also took a follow-up workshop in 2007 on how to write curriculum within the modeling framework. I became a workshop leader myself from 2013 to 2017, so I did it for 5 years. I'd still be doing it if it weren't for the change from No Child Left Behind, Every Student Succeeds, altering funding for that. So I'm going to start by giving you a brief overview of modeling instruction in case you're not familiar with it. I'm not going to go into a lot of detail. It was primarily developed in Arizona by an Arizona high school teacher named Malcolm Wells in 1990. He'd been a teacher of 30 years at that point. He was under university guidance by Dr. David Hestenes, who's still alive at Arizona State University, and this was part of Malcolm Wells' PhD work. It's pretty much a guided inquiry approach. Carefully chosen situations are presented to students, and then they're asked to investigate and come up with a quantitative model to describe and be predictive about that behavior. After the beginning of the course, students are generally not given prescribed lab procedures. They have to create their own investigation, isolate variables, multiple trials, all that kind of thing. And then the post-investigation involves a class debriefing and discussion to make sure we're all clear on what the model is. And then they deploy the model. They do worksheets, they do card sorts, ranking tasks, and then eventually deploy the model in lab practicals and summative assessments. It's not dissimilar from other guided inquiry approaches. It's, say, one of several. I'm aware of IL and POGIL, I'm not sure how to say that, that are not very different. So my talk is on the strengths and weaknesses of modeling instruction, and it's mostly strengths. So it's cognitive-based. I'm going to start with strengths. It's cognitive-based, and it mimics how people learn, observe, measure, analyze, and conclude. And I'll give you a little story that I noticed actually right around the time I was taking the workshops. I had a very young son at that time. And a little bit before, he was sitting on the floor in our living room, and he was picking up a ball and then dropping it, and then he'd pick it up again and drop it, and then he'd pick it up again and drop it. He did it several times. And what I concluded that he was doing is he was making sure that that ball fell the same way each time, every time. So he was developing sort of a conceptual model of how things behave after you let them go from a height. And that's kind of what we do. We observe behaviors and try to develop mental models that are predictive. So that's one of the real strengths of modeling instruction, is that it mirrors that very natural cognitive process that we all do. It also encourages scientific inquiry and discourse, where students make observations, then they come up with an idea of what to investigate and how to measure it. Take those measurements, and then they analyze those measurements with graphs or whatever, and then have groups within, or discussions within their groups. They have discussions between groups until they can come to a scientific consensus. And it has to be evidence-based. It's very hands-on and engaging, where students start every topic with a lab. And I have had students who struggle or don't care for science or whatever tell me at the end of the course that they really liked it because they weren't just sitting there. They liked doing science rather than just passively sitting and trying to take it in. It's also socializing. They have to learn to work with people that they may not like or get along with. I try to mingle up the groups. Most modeling teachers do, changing jobs and so forth. And research indicates, a lot of research indicates, that there's very strong retention. 90% is still retained, at least after 1 year. And we measure this using the force concept inventory, pre-tests, post-tests, and then test them a year later, and retention is very strong. This compares to, say, a more passive method, like just straight on lecture. I'm not counting where there's more interaction, but just teachers talking to students. That's about a 10% retention. So we have a huge benefit there. Now, what are the problems with modeling instruction? Well, everything has its price, right? So doing labs and talking and all that is very time consuming. It's hard to get through what's considered the traditional curriculum over time because you're doing so much on top of that. And it gets better when you become a more experienced modeling teacher, but it's nearly impossible to cover the same amount of material in the same amount of time. Sometimes you get snafus with labs where the whole class might get pretty bad results, and then you have to go back to square one and have discussions about, well, how did we measure this? How could we measure it better? And that can be a plus because students get they get more steeped in how science is really done. Something doesn't work out, well, go back to the drawing board and try again. But then again, that eats time, and we're supposed to cover certain curriculum, and that can be a problem. So time is a big issue, but what I used to say when I taught the workshop is, let's say you get through 80% of the curriculum, and when you're a beginning modeler, it's going to be less than that. And let's say you retain 60% of that. Now, as I've said, retention is generally closer to 90%, but let's be conservative and say 60%. And so is 60% retention of 80% of the material? How does that compare to 10% retention of 90% of the material? And so even though modeling you're covering less material, the retention of what you do is much better. Another issue with modeling, which is not unique to modeling, is it takes a very skilled teacher to successfully implement it. You have to be on your feet, you have to be moving around, you have to be asking students the right questions. When they're working on the labs, you have to monitor them, talk to them. What are you learning? What are you getting? You can't just sit there at your desk and sip coffee and watch the world go by. And the teacher must be trained in the modeling approach. And that brings up another issue with modeling that I'll hit a little bit later. There's also a technology barrier with modeling. It can be done with meter sticks and stopwatches and mass scales and so forth. But again, that takes even more time. It's most efficiently done with electronic data collection, like Vernier or Pasco equipment. And some schools can't afford that, don't have that. So there is sort of a barrier there that can inhibit adoption of it. It's often conceived of as, or perceived as a curriculum rather than a pedagogical approach. And so even though there's curricular materials available from the American Modeling Teachers Association in Arizona State, so we have teachers who get a hold of that and they use it and say, well, I'm a modeler, but they're not using the modeling approach at all. And then that undermines the impression of modeling in the community at whole. And that's something the American Modeling Teachers Association tries to keep a lid on. And I want to emphasize right here, if you've been exposed to modeling or if you haven't, it's not a curriculum. It is a pedagogical approach. My practical science class, I have developed within a modeling framework, and I use very little or none of the modeling curriculum that's been developed. I developed my own. Now, one of the other huge weaknesses, and it's not a weakness in modeling itself, it's a weakness in how it's being given out to the education community at large, is training is almost always for in-service teachers. And it's usually a workshop, and it's time consuming. Some of them are as short as a week, but you really need 2 to 3 weeks, so 10 to 15 days of time in workshops in order to sort of get it. And having done 3-week workshops, it usually takes at least 7 days before people start seeing that it actually works. And then the next 7 days is they're trying to figure out how to make it work for themselves. So it's difficult to penetrate science education community from that because of that workshop commitment, which lends to another problem is outsiders tend to see modelers as sort of cultish and insular because you have to take this special workshop, and I'm sorry, you kind of do. And that's kind of a self-inflicted wound on modeling. And there's a lot of talk about the founders and so forth, and it's probably time to move on from that and keep pushing it. Now modeling has been developed originally for physics, and then it was pushed out into chemistry, and now biology, astronomy, environmental science, and I don't know what else, but that's the last I heard. I've only taught it with physical science and physics, and it adapts very well. I have colleagues who use it for chemistry, and it adapts pretty well there, although a lot more by analogy rather than direct measurement of actual phenomena. And then my friend who teaches biology and environmental science in the modeling framework says it's more of a forced fit there. And I can't really comment much more on that. Coming back to the cult status issue that I brought up, we're not going to lose that until modeling penetrates schools of education and becomes part of science teacher training. It doesn't have to be modeling per se, but any of those kinds of approaches, modeling-like approaches. And I'm not aware of how much that's really penetrated schools of education. It hadn't for me, but again, I graduated from college in 1990, so it wasn't really there yet. Another issue with modeling instruction is it changes the rules of the game of school for students. Typically, like in my AP class, we get some high flyers in there, but they got there by figuring out the rules of the game of school. And they're either naturally good memorizers, or they can go home at night and study the notes they take and memorize that so they can spit it back at me the next day. And modeling doesn't work that way. They have to conceptually grasp it. And that's a bit of an adjustment period. It can cause some anxiety, it can cause some stress, it can cause some unhappiness. And you have to really work students in slowly and gradually on that, and very gently. And you can't really gradually do the modeling process, but you can lower the stakes at the beginning a little bit. And tying into anxiety, I mean, I've been a teacher for 30 years, and I've seen anxiety become more an issue within the classroom. And changing the rules on them can be an aggravating factor for that. And so you have to be very careful about how you construct your classroom culture and maintain it so students feel secure and safe. I had a student last year in physics, did the best in the class by the end actually, but highly anxious because I changed everything up on her and she wanted to get an A, and there was a lot of figurative hand-holding in there, not literal. So one way around that is when students are working, you can go to that student and talk to them, say, what do you think what's going on right now? And talk them through the process. And if they're right, say, great. When we have the whole class discussion, I'm going to ask you to contribute. So I want you to be ready for that. And you can gradually have students do that while lowering their anxiety. But the modeling teacher skill is absolutely paramount. One of the other weaknesses is if you get some students that like to dominate the conversation in class, what happens is the quieter students, the shyer students, the less confident students sort of hide behind them and learn to parrot what the more confident students say. And so the teacher has to constantly monitor the whole class and bring out responses from the quieter students before the more confident students can tell them what to say. Because of the time demands, as I said, less curriculum is covered. But also, as I said, what is covered is generally much better understood by most students, and this is borne out by FCI results. And really, modeling demands a really skilled teacher, one who's really willing to examine what he or she is doing and thinking about how to improve constantly. And that's not really a weakness, but that's certainly a demand of it that maybe straight up lecturing doesn't bring about. So that's my talk. That's what I have to say about modeling.
All right, thank you, Chaz. I see we've got a couple of hands up in the. Anyway, we have a question from Kevin. Please unmute and go ahead.
Thanks. I apologize if you addressed this. I had to step away for a moment, but like a lot of us, I'm sure, I teach seniors, and especially my school, well, maybe not especially my school, but they've had their whole career of very traditional classroom instruction. And anytime that I've tried to step away from that, I get a lot of, well, maybe not a lot, but I start hearing, oh, he doesn't teach us anything.
No, I got that at first.
Yeah. Well, how do you combat that or try to push back and let them see that they are learning, just not in the same way?
So I said this in a comment off to the side in the chat yesterday, is I try to make everything I do transparent with my students to get, and I found it helps with buy-in. So I tell them up front, I'm going to be changing the rules on you, and you may have some anxiety about that for a little while, but I'll help you through it. Excuse me. And this is why I'm doing it. And I'll talk about retention, and I'll talk about performance in college. And especially in the beginning of the course, where everything I'm doing is new to them, is I explain to them either before I do it or right after, so that you have kind of an aha moment, is why did I do it this way? And then they start to think about, why is he teaching this way? And you get a lot more buy-in that way. And I haven't had as much of that, he doesn't teach us anything kind of thing. But in the first few years that I was a modeler, I got that all the time.
Thanks. I imagine I like to really focus, especially the first week, on building relationships with my students, and maybe that establishes the trust to try something new. And then once you sell them on the idea, you keep hitting that, then between your relationship and your rationale, maybe you get some more buy-in that way. I like that. Thank you.
You're welcome.
Thanks. And Terry, you're up next. Please unmute.
Hey there. I just wanted to jump in on one of the little things you said that Daisy changed to Marie too, which is about sort of drinking the Kool-Aid. I've been to Arizona State for the modeling training a long time ago, took a second class with it too. And two things that I think teachers find intimidating. Number one is the notion that you need to be an expert teacher to make it work. And I think I want to reverse the statement a little bit and say it will make you a better teacher.
I'll agree with you.
If you're willing to put your time in, it'll make you into a better teacher. So again, this is sort of the target audience of going, clearly we're all here because we want to be better teachers. And on the flip side of that, let me just say that you don't have to buy into this like 100% to make it work all the time. I also teach AP. Mm-hmm. And I feel like you've got to pick your moments of this section, this thing. I'm going to do it modeling style. And maybe other things you have another excellent way to do them. And I think that we end up experimenting in our own classrooms a little bit and going, I did it this way this past year. I did it very modeling and it worked great, and I can refine it and make it better. And sometimes it's not going to work out great, and you're going to have to revise it for your next audience, and that's okay too. Mm-hmm. But I agree with what you said, that this isn't about, oh, here, let me hand you this packet of worksheets and you should work through them. It's really about method. And Marie said that she sort of started doing this on her own and found out later on that there's people who are like, oh yeah, we've got training on this thing.
Yeah, I actually, before I took the modeling workshops, I was attempting a modeling approach, and I found I was actually missing a pretty key component. And once I took the workshop about a week in, I'm like, oh, there's the component I'm missing, so I'm good. But I kept with it because I wanted to refine what I knew. But yeah, and you know, my predecessor, who taught me physics, and then I replaced him as a physics teacher when he retired, Roy McCullough, he said to me, teaching is an experiment. You have to try things, and not everything's going to work, but then you'll find out what does. So I'm not saying you have to do exactly the modeling curriculum, but you find stuff that works well, and you've got to reflect on what you're doing.
I agree. And since there's a research base on it, and since we don't want, particularly, I've met a bunch of new teachers at this event, right? And we don't want you to have to stumble and figure everything out on your own, because there's been teachers who've come before you who have found a decent way to make it work. And there's no harm in trying it out and going, yes, this really worked for me, or, oh man, that one didn't work out.
Yeah.
That's it for me.
Great.
Thank you, Terry. Brock, you're up next. Unmute, please.
I was just hoping I could, and we probably don't even have enough time, but I was hoping I could discuss how you modified your problems, because I wrote in the chat that I find that the provided problems sometimes are a little bit too complicated. And then there's also times where I feel like there's too much math. And I wanted to ask you your ideas on how you've modified problems, because you said you made your own or created your own.
Well, I took one class, yeah. For my physics courses, I still rely heavily, but not entirely, on the curriculum materials you can get from the modeling instruction folks, but I always modify it. But I came up with a whole class called Practical Science. It was a conceptual physics class, which means little to no math, and developed a curriculum on my own that I tweaked every year and still tweak every year and try to tailor it to that year's audience. So, you know, and that's what I guess I'm going to say to you is, you know, you have to gauge where your students are and meet them where they are. And
yeah.
You know, that those worksheets that you can get from the American Modeling Teachers Association and so forth, they're Word documents. They're not carved in stone. You can change whatever way you feel is appropriate. I think on a lot of the tests they provide, most of the questions are pretty bad. And
yeah.
So you just start working on fixing it and doing it the way you want it.
Well, my thing is I teach at a small school. I'm the only physics teacher, and so my physics class is basically introductory class, and there are some kids that can do the math and there are some kids that don't. So I try to make assessments that don't have as much math and are more conceptual. Then I try to make tests that have some math for the kids that can do it. And I didn't know what your or other people on here's opinion would be about an introductory physics class that I don't have AP, I don't have conceptual physics, I just have physics. And how much math should I put in it? I mean, it's algebra based, but still kids struggle with algebra. So
as much math as you can get it through them successfully, I would say. And you know, you push them too hard, you lose them.
Yeah.
And something to investigate there is I also tutor math on the side for a little extra money. And I have found that students who have trouble with algebra, you got to walk them all the way back to fractions. They generally don't understand fractions. And when I find that, they don't understand fractions because they don't know how to multiply and divide by hand. So they don't know what it means. And so maybe start some conversations with your math folks about that. Yes, I know exactly why you're chuckling. That can be dicey, but kids who have trouble with algebra, generally it goes all the way back.
Yeah, sometimes I notice they can't do the simplest things, and I'm like, holy cow.
Yeah.
And we need to move on right now. Now, Shuyi, I see that you have your hand up. We need to take a quick break here, although first, of course, we should give thanks to Chaz for his wonderful talk.
Oh, thank you.
But Shuyi, if Chaz is willing to stick around during our break,
Sure.
then maybe you could ask your question of Chaz while everybody else is on break. I'll stick around for that. And everybody else, I'll see you back at 11:17, let's say.
Chef, my question is really about modeling for a diverse group of students. And I think that's one challenge as teachers, always
By diverse, you mean by ability?
Yes, so we have 24 teachers, science teachers in our department. So we have levels, classes are leveled. So 9th grade physics are kind of leveled into 2 different courses. And whereas I find that it's much easier to talk about modeling and teaching pedagogy and kind of active learning with students who have the math ability, And when we have EL classes, kind of more special ed group students, it's intimidating. To talk about how to approach and how to lead discussions in those classes where probably most of the students don't know any algebra and are afraid of math or are afraid of discussing their mental models in the class. So I'm interested to hear more about your.
When you begin your classes, like the first week or so, what do you start them with?
I usually do some kind of engineering activity with my students.
Okay, so what do you do for your first lab where they might have to know some math?
I've done different things. Sometimes we do kind of measurement with looking at speed of different vehicles, and sometimes we'll go back and forth. Sometimes we decide all together and start with kind of exploring forces, kind of force concepts.
Okay, so what I recommend then is back it down. First couple labs I do with my students, except for AP, is I'll take a large rubber ball and I'll drop it in front of class, and I'll do it from different heights, and I ask them to give me observations. And somebody says, you know, it bounces back about the same amount of the drop height every time. Like, are you sure about that? Well, no. So how could you measure that? And so then they collect data. And I ask them, well, what's your conclusion? And then they don't know. I'm like, all right, well, you know, how could we maybe put this in a picture that might make it easier to understand? And I'm like, well, okay, let's graph it. So then they graph it and they get a line with a slope. And if they don't do too wide a spread of data, they'll get a fairly linear graph. And ask them to draw a line. And depending on the level of student, it's either best fit or just, hey, best guess. And ask them what the slope of that line means, and you can get into conversations about what that math means without doing it like right into constant velocity. Break them in, sort of, with a lab like that, where they can see that. So then once we have those conversations and we get sort of a mathematical model for dropping a ball, you can, depending on the class, you can either continue with that and drop it from a higher height, and they predict it, and if it's within a certain percentage, that's great. What I do with my more advanced students is I drop a ball from a very high height, because that graph is actually a curve, and it breaks their model. And then we say, well, our model is only good for this spread of data, but it's pretty accurate there. So it depends on where you want to take the conversation. But I suggest you back it down and introduce them to what that's going to, the lab procedure, and then making a graph and what the graph tells you. Just do it a lot more slowly at first. And it's going to feel like you're crawling, but you're going to make up time later on, because then you're not going to have to do that. When I taught the modeling workshop, I mean, people are like, oh my God, this is so slow. And like, yes, but the further along you go in the year and the more used to the process they are, it goes faster and faster and faster. You don't have to go over experimental procedure every time. You don't have to go over how to get data or what the data tells you every time, because they start adapting to it.
That's useful. Thank you.
You're welcome. All right.
We're going to resume again in just a moment.
Oh, and thanks, Jeremy.
Thank you, Chaz. All right, so hopefully everybody is back now from break. And we are going to transition now to our third speaker for this session. Our speaker is Marcy Williams from Ooltewah High School in Tennessee. And Marcy will be speaking on developing local physics teacher training.
Hi, I'm Marcy Williams. I am a physics teacher at Ooltewah High School. My high school is a public high school outside of Chattanooga in Hamilton County, Tennessee. And I'm going to be talking to you today about a workshop that I put together for some teachers in our region. And I want to just share with you sort of how we got started with this workshop. So 7 years ago, I left my job as a biomedical engineering postdoctoral fellow at Harvard Medical School to teach high school. And I saw it as this amazing opportunity to interact and impact the lives of young people. So follow that up with a big dose of reality. Surprise, not all of my students were exactly like the ones I had encountered at Harvard. My students could, from the very first day, recite to me, objects in motion stay in motion unless acted upon by an outside force. But they really didn't understand what that meant. And as a new teacher, I struggled to give them experiences that would help them to develop a true understanding of Newton's first law. I also faced many struggles that new physics teachers especially face. For instance, you may have very little laboratory equipment. Some of the equipment that you have is a complete mystery, just pieces, parts here and there with no manuals. A lot of times the textbooks and class materials that you have are just insufficient. And then most people haven't had this particular level of physics since they were about 19, and I know that was certainly the case for me too. And then I think the worst thing for new physics teachers is that there's no one you can ask for physics teaching guidance, because usually you're the only physics teacher in your classroom, or maybe even in your district. So coming from a research background, I decided that I should use my research skills to help me sort of figure out this problem, right? So picture me in my classroom alone on a late afternoon trying to figure this out and Googling how to teach physics. Now, this is probably not your best source of information, but it turns out there's a lot of resources on the internet, and I found lots of great things. I found PhET labs, I found simulations, I started reading blogs, and I started, looking at Twitter, and I really did improve my teaching, but I kept coming back to, I want to be better at this. And then asking myself, how can I get better? And finally, the realization I came to was that I needed more training. And so in seeking out training, I found some modeling courses that I wanted to take, but I had a problem. They weren't offered in Tennessee, and they were offered over the summer, and they were about 3 weeks long. And I wasn't sure how to get that accomplished, but I applied for a grant from this organization, Fund for Teachers, and they gave me the funding that I needed to be able to spend 3 weeks out in Arizona taking this course 8 hours a day with all physics teachers and really learning what it means to become a good physics teacher. And I took that back to Tennessee, and I was really able to put those lessons into action, and I felt like my teaching vastly improved based on what I learned there. And then I started to wonder, well, what about everyone else? There were other physics teachers in our area that just didn't have the opportunity to go to Arizona for 3 weeks, right? So when you start to think about professional development for physics teachers, it's often not available. But it becomes really important when you look at who is teaching high school physics. So this is some data from 2013 from AIP, and they looked at which teachers had a major or minor in physics if they were physics teachers, or a major or minor in physics education. And then over here, this is the total for these different years. And what you can see is that less than 50% of our physics teachers actually majored or minored in physics or physics education. So this doesn't mean that teachers haven't taken physics classes. Of course they have, right? I also don't have a major in physics. I took lots of physics classes, but I certainly never had a class on how to teach physics. And that was something I felt was lacking. When you also look at what physics teachers teach, over here in this chart, you can see for different levels of teachers, either they're new or even some specialists, they went through and said, what percentage of classes do you teach that are just physics? And you can see that from the gray bars, these are teachers who teach mostly something that is not physics. The pink bars here are teachers who teach equally half physics and half something else. And you can see that most of our physics teachers are responsible for teaching something other than just physics. And so this means that their time is divided and there's limited amount of time they can spend on this material, right? when you start to look at physics teacher training from a point, from the perspective of equity, this becomes even more important. So here, this chart is also from AIP, and it is from 2013 again. And it basically shows the proportion of students in each group that are taking high school physics. And if we look at Asian students, you see that over 50% are taking high school physics. And for white students, over 40%. But for Black and Hispanic students, it is less than 30%. And sometimes, I'm not sure, there's lots of reasons for this, why this occurs, but sometimes this is because the schools where Black and Hispanic students are attending don't even offer physics because they don't have a teacher who's properly trained to teach physics. This becomes important also when you look at some data from ACT, and they started to look at college and career readiness for students. And they looked at standardized test scores as well as performance in their first 2 years of college. And what they could see was that students who took biology, chemistry, and physics performed better on their standardized tests and in their first couple of years of college. So these are important classes for students to have access to. It's even more interesting when you look at the state of Tennessee. We recently changed our standards, and when we did, our state was offering summer training, and they offered summer training for biology and chemistry teachers, but there was no training offered for physics teachers. Wah, 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 right? So I started to think about what can I do to help this situation, because I truly believe that all teachers need access to high quality professional development that is aimed specifically at their courses. I decided to put together a workshop, and I had this idea that we could meet 2 Saturdays a year. Yeah, it wasn't the 3 weeks that I had, but 2 Saturdays a year. And if I could get 20 teachers, then if they each had 150 students, we would reach 3,000 students over a year, right? But I knew that I needed some things to get this started. My idea for the workshop was that I wanted to reach teachers exactly where they were. So I wanted to present them with material that didn't mean they had to go out and buy some new equipment. So we focused on really low-tech solutions, and anything they needed, I wanted to supply so that they could put this training into action the very next day in their classroom. So for instance, we talked a lot about how to use whiteboarding to help with discussions in small groups, right? So I provided them with whiteboards and markers. We talked about how to use card sorts, right? So I made sure that they had a class set of card sorts that they could use the very next day. I also wanted to be sure that I could feed them. So here's our apple, because you know, you ask somebody to come for 5 hours and spend time with you, you gotta feed them at least lunch, right? I also needed some money because I felt strongly that I could organize the workshop, but I didn't feel like I could do a good job in both organizing the workshop and leading it. So I needed some money to pay for a workshop leader to at least say, hey, we appreciate your time that you spent with us. And then the other thing I needed was context, because I wanted to have 20 teachers there, but I didn't even know 20 physics teachers. So I started to get this workshop together by essentially applying for funding. So this is a picture of me at Pitch Night for Teacherpreneur here in Chattanooga. And this is a group of investors that support education in our area. And I pitched them my idea to start up something called Physics EDU. And they liked it enough to give me some money to get started. I made up a flyer, and the next step was really like, how do I find people to come? I looked at a map, and we are in Hamilton County, Tennessee, and I basically made a big circle, and I listed all the counties around us, including counties in Georgia, and I started reaching out to whoever I could. I reached out to superintendents, principals, department chairs, and any physics teachers that I could find email addresses for on the internet. And honestly, a lot of places don't publish email addresses, so it was a little bit complicated to get access to the physics teachers. I also reached out to private schools because I think it's important to involve our private schools as well in this kind of training. we had good attendance. So we ended up having 18 teachers attend. They came from 7 different counties and 4 private schools. And I think what really speaks to it, we've had 2 workshops so far. In the first workshop, we had 16 teachers attend. And in our second workshop, 15 of those 16 teachers came back. So I can tell you that it was very successful, and they were very appreciative of the what we gave them and the instruction that they got while they were there. One thing that made it really successful was having a great workshop leader. So I was able to recruit Dr. Brian Frank from Middle Tennessee State University. And this really happened just because I had been following him on Twitter, and I realized that he was an amazing physics education leader, and he was only 2 hours away from us. So I reached out to him and asked him if he would be willing to lead the workshop, and he graciously agreed. And I think that really made the workshop great, because he's really good at teaching teachers how to set up a classroom climate of engagement and discussion. Then here's some pictures from the workshop itself, and you can see that we have a really nice space here, and that is because we were able to get a community space that's available for different organizations in our area and use that for free, which was really helpful as well. After the workshop, we asked our physics teachers some questions. They filled out a survey, and we asked them, how often does your district or school offer training that is designed specifically for physics teachers? And these are the results. 80% said that their school or district never offered training for physics teachers. And this was just shocking and really helped me to see how important it is for us to offer this kind of training to our teachers. We also asked them what they liked most about the workshop, and we got some great feedback. They liked things like, they said, lots of great ideas and things I could take back and use in my classroom immediately, which is so important. They provided resources that allow me to immediately implement ideas and strategies. They said they liked this, that it was specific for high school physics curriculum, and the chance to meet other teachers, right? Because we can't just work in a vacuum. They said it was much more directed and useful than our typical PD sessions, because it focused on something other than just reading the standards, right? Ouch. Then we asked them, how do you hope to change your practice as a result of this training? They said, I want to engage students in large groups and small group discussions. Yes, that's exactly what we want. I will be engaging with evidence. Yes. I hope to give students a chance to develop understanding of the concepts through discovery instead of me lecturing. Yes, less lecture, right? Adding motion diagrams to my curriculum and increasing rigor. Isn't that what we all want to do? Like, increase the rigor without just blowing our kids out of the water. So the next steps for our workshop, we're holding a virtual workshop in August, which it turns out this is really amazing timing for us because we're out of money, so we can't really afford to have an in-person workshop. But a virtual workshop will be great. And we're going to cover things like Desmos card sorts, pivot interactives, breakout rooms with Google Slides, using group work on motion and force diagrams. Also, we're working on acquiring additional funding so that we can have future in-person workshops. And then we are expanding our audience by reaching out to additional districts and private schools. So I hope that I have convinced you that we are actually better together, and maybe some of you will take this a challenge to go back and prepare a workshop in your district or in your region, because then your teachers will have access to teacher-led training that is for physics teachers and by physics teachers. Thank you.
Thank you, Marcy. I have one question for you. Before we get to the hands up. You had a workshop 1 and a workshop 2. Can you just run through, if maybe I missed it, but like what times of year were workshop 1 and workshop 2, and what kinds of things did you do in each of those 2 workshops?
Sure. So in the very first workshop, it was the very, very beginning of the year. So my district had started back maybe 3 days, and then we had the workshop. And we did that intentionally because our content that we wanted to focus on was really like starting with just basic motion maps and a little bit of graphing, like position versus time, but really looking at multiple ways of depicting motion. And so that was the first one, and we wanted the material to be something they would use immediately. So we felt like we needed to do that early in the year. For the second one, I kind of wanted, we had some debate about whether we should continue, like sort of in the next thing would have been like either looking at acceleration or maybe forces. But when we polled the teachers that were involved, they actually wanted to look at electricity because they, I think, felt the most uncomfortable with that topic, and they wanted some ways of talking about circuits. So we really focused on circuits, and Brian did an amazing job in that one on looking at potential difference and how to use potential difference in your circuit representations. And yeah, so that was just sort of by choice.
Okay, thank you. That's helpful. We have a question first from Rob. Please unmute yourself.
Hey. So I've been looking a lot into actually isolated physics teachers and very into the data that you're discussing. And recently we just put out a paper that goes with what you're saying, that the certification of a teacher, a physics teacher, actually doesn't matter. It's their professional age that matters. But the question I have, what you've been working on has mainly been around where you're located, correct?
Yeah.
And it hasn't really, or you haven't necessarily had the opportunity to go elsewhere to other states?
Right. So I just focus on Southeast Tennessee and Northwest Georgia. And I feel like that's for a couple of reasons. I don't think most teachers feel a need to travel very far for their professional development. And I also really feel strongly that teachers in your local region need access. And so while you can host, maybe something at a bigger scale, that really requires teachers to travel, which if, at least in Tennessee, we just don't get money to travel to conferences or anything like that.
No, like what we don't either, and we have a sort of similar group that meets like that. But it's kind of the first time I've heard of a solution to a problem that we've sort of have going on outside of where we are. So I'm probably going to reach out to you. Thank you.
Sure.
Thanks. Clay, you're up next. Please unmute yourself.
Hi, I'm Clay Stanfield, and I'm kind of doing the same thing in northeastern Texas, trying to get a community of physics teachers going. And I was wondering if you had any insight on how to get teachers those credit hours approved in their district. Like, do you have regional service centers like we do here that the districts kind of rely on to filter out the trainings that teachers go to, or what insights you might have with that?
So we don't have any kind of like governing body other than like our district itself. If they call it a professional development, they'll put it on, like give you credit for that. I will say, in talking to Brian Frank, that other workshops he had led, we didn't go this route because none of our teachers were really asking us for it, but other workshops he had led, he basically had it sponsored by his university, and so he was able to get sort of credit for teachers because it came from a university. So sometimes having somebody with a different credential or can help, but yeah, we don't have as many like issues with does it count for certification or not in our area.
Okay, thank you.
Thanks. Doc Roth, you're up next. Please unmute yourself.
Yeah, thank you. It's really inspiring, and I sure wish I had a program like yours to attend when I was getting started. Even now, about 10 years into this career, I would benefit from this experience. One thing I was wondering about is in the case of modeling and other inquiry-based teaching, we had this discussion of the tension between how much you can cover and how deeply. And this dilemma sometimes hits us even more strongly in PD because you have a really short amount of contact time. Online might change that up a bit. But a very strong PD I took from APT a dozen years ago was done where we were taught the way we were told to taught high school students. And that guy actually was doing direct instruction, but leaving aside the particulars, his point was that pedagogy is content. And when you teach teachers, you want to teach them. In other words, when you go to a training and they show you PowerPoints for 2 hours about engaging students in active learning, there's a contradiction. I don't think anyone does that now, but what I'm curious about is if this tension between trying to put as many resources in the hands of your teacher learners as possible and versus having them live the slow experience with blind alleys and dead ends of maybe an inquiry-based module. I'm wondering if that was a tension and if you've come away with any insights on how to sort of resolve that.
So for sure it was, because when I went with my big idea to Brian and said, hey, can you please lead this workshop? He asked me what we wanted to cover. And basically I gave him like all of my standards for, physics. And I was like, okay, you got 5 hours, cover all of these. And he, laughed at me, and quickly we sort of settled on a much smaller version, but we focused on motion, and we really just focused on constant velocity. We didn't even talk about acceleration at all. And it seems really small and maybe frustrating to some of the teachers because they feel like we're only getting a little bit. But the things that I think you have to focus on more than just the content itself is how to deliver the content. Like I love the talk this morning about, or was it this morning, yesterday? I think it was Jeremy, yours. It was about how to question students, right? And so we focused a lot on just like discourse with the students and how to lead groups. And so even though maybe you didn't cover every piece of content, you've given them a new way of interacting with their students that maybe they hadn't seen before. So I think if you can focus on that more broadly and then pick specific areas that you're interested, I think that helps.
Teach a teacher to teach a student to fish.
There you go.
Thank you, Doctor.
I like that. And we've got a lot of questions. I'm going to try to get through as many as we can.
I have question.
Nikolai, can you raise your hand, please, to get in the queue?
And
I'm sorry, Nikolai, we have a lot of people who already have their hands up. So put your hand up to get into the queue to ask, please. Rebecca, you're up next. Please unmute.
Hello, I'm from University of Houston, and Margaret Chung and I are both here. We have a very similar professional development program for teachers here, and a whole lot of our teachers are actually in the session. So hi, STEP physics teachers. Marcy, your program sounds great. We used Physics by Inquiry by Lillian McDermott. Our program was originally funded by the state of Texas, and that funding has gone. So we are actively looking for new sources of funding to renew the program. So who all, I don't want to compete with you, but what sources are you looking at for funding?
So I think that's one of the hardest parts, right? Is finding the money. And so, I was so blessed that we have a local organization that would fund me, but it's gone, right? So then the question is where to go next. And honestly, that is still up in the air. We're looking. So there's national organizations, but, that's hard to get funding from. I'm also looking at some of the local Tennessee organizations to see if they have funding. One thing that I found with this workshop is it was so great. A lot of our money went to supplies, right? Like I said, we bought whiteboards and we bought a lot of things for the teachers. But now that we've kind of hooked them in, they really like not just the stuff, but like what they're learning. I feel like we don't need as much for the next couple of workshops. We don't have to give them as much stuff as we maybe did the first couple of times. Although I would love to give them stuff and supplies, right? But if we can't, I feel like they'll still come because it was such great instruction.
Okay.
Thanks. And let's try to squeeze in one last question from Jolene.
Okay, thanks. I loved your talk. I have two parts to my question. One part is I'm just wondering like how you partnered to recruit people. So like, did you use the local AAPT chapter, and is there any way that you're like tying them in bigger organizations to keep everyone kind of involved? And my other question is about if you did anything to look at like building relationships with students or looking at diversity, and if you have heard of Step Up, the program that's designed to encourage women in physics, because they have some trainings that might work well, and ambassadors could come lead that in your workshops.
Oh, that's a cool idea. No, we didn't do anything on diversity or Step Up, although I feel like in terms of like establishing community in the classroom, anytime you're using like good discussion, it starts to establish that community. And then in terms of contacts, we don't have a super active AAPT, especially at the high school level here. So I honestly, that was probably the hardest part, was finding people that would come. We have about 10 physics teachers in my district, but I knew most of them wouldn't come to this event just because of where they're at in their family lives / commitment / interest in extra PD, right? So I really just had to reach out to everyone, and there was the only way to find contacts. Honestly, I went to every school district and I Googled their, to see what email addresses I could find. I looked for their principals, their assistant principals, their department chairs, their, anybody. If I could find an email, I sent them. And I think that probably some of them thought I was like a scammer because I'm sending out like asking people to go to like a free PD, and they were probably like, what is this? But yeah, I just started emailing people.
That is excellent. Marcy, your talk is very popular. There are a lot of people who want to ask you questions, but to keep us on our timetable, we need to move on and go to our break. Marcy, Eric created a Congregate table. I think he called it Ask Marcy. So I'm going to ask you if you would be so kind as to go to that table when we go to Congregate, and the folks who still have questions for Marcy, and I bet there's more than 3 remaining probably, we can talk to Marcy more on this really important topic soon. So let's all thank Marcy for her presentation.
Thank you.
And thank you very much. And it is time now for a 15-minute break. We're 2 minutes behind schedule, so we'll be back at 12:02 Eastern Time.